So I'm keeping my own timer.
Yes.
So, alright, so I'll start my timer now. So because the time is short, I might skip few slides and be a little fast, so please excuse me for doing that. So we are going to talk about integrated passive seismic for exploration. That's the topic. I represent Parsan. It's an ISO certified company. We are basically a geophysical company. We're the largest geophysical company in the field of near surface geophysics, so engineering geophysics as we call it. And more than being the largest and everything, we are known for bringing various innovative technologies from time to time, starting right from 96 when we got GPR, then shear wave refraction, etc. 2008 was the time when we introduced the passive seismic tomography for oil exploration along with our partners, Landtech and Seismotech at that particular point of time. And our main strength is our people, of course, who have high experience. So we are working in India, Bahrain, Saudi Arabia, and Singapore. We have our own offices, so we are Indian multinational. And we are working in more than 14 countries around the world. Very briefly, I am Sanjay Rana. I am a geophysicist by profession. I graduated in 1990 from University of Roorkee. I did my MTech in applied geophysics from there. Had a brief stint with UP government, then Department of Atomic Energy for some time. 95 I left from there and turned an entrepreneur, and since then I'm working in the field of geophysics. That's a very brief I want. So now coming to the topic, passive seismic tomography for exploration. So the idea of using these earthquakes to find out the subsurface geology is not new. It has been used by various research institutes and universities to have an idea of the regional geology of the area. But in this, what we are doing is we bring from regional seismology to exploration geophysics. That is what we are doing. Now in this, the receivers are being planted in a very dense network. So standalone recording system with frequency range of 0.1 to 100 hertz, and they are continuously recording receivers. And the sources are naturally occurring seismic signals. So for example, we can have pure ambient seismic noise, we can have local, regional and teleseismic events occurring during the recording period within or around the area of interest. So that's the basic, that's why we call it passive, because we are not involving any active source in this. And when we say passive, we are making use of the naturally occurring earthquakes within the study area, teleseismic events around the area, and also the natural noise, ambient noise, which is present in the area. And that's why I call it integrated passive. It's not just one particular part of passive, but integrated passive. The main target is to create a 3D structural and lithological characterization of the area of interest. So what we are trying to create is a VP model and VP and VS model. That's what is our idea. So we have a structural model and we have lithological model of the subsurface after doing all this, what we are doing it. Now when we talk of low frequency in seismic exploration, as we all know, like we have active seismic exploration 30 hertz plus, and then we have passive seismic which is lower than 30 hertz. Now of course these low frequencies have the potential of seeing much deeper into the subsurface, but difficult to produce when we talk of active seismic because of various reasons we already know about. So once we talk of 0 to 30 hertz comes the integrated passive seismic, in which we have ambient noise, then we have surface wave from teleseismic events, we call that surface wave tomography, this ambient noise tomography, and then we have local earthquake tomography that we call LET, and then we have micro earthquake based on micro earthquakes, and we have reflected wave passive seismic interferometry. So all these techniques together we put as integrated passive seismic techniques. The best part is that all these methods are utilized on the same data which are being collected by the same set of receivers. So for example, we are putting the receivers on in the ground, observing the data, and then extracting the required data for all these different processes. So this entire integrated thing is happening with the same data set. So the concept is when we say earthquake based is local earthquake travel time tomography, reflected wave passive seismic interferometry and surface wave tomography, and noise based of course is ambient noise tomography. I'll just go one by one in very briefly. So this is the type of passive seismic signal exploited in local earthquake tomography is P and S wave travel time of local earthquakes. So what we are doing is we have these sources. So sources are under the subsurface. This is our subsurface model, let's say divided in the unit blocks, and these waves are traveling through the subsurface being received at the stations, and ultimately by picking the P wave arrival time and then the S wave arrival time, doing the tomography, we are creating the VP model. So this is the VP model which gives you the complete structural control. You have the VP upon VS cube which gives you information on the lithology. Then you have accurate seismic event location, and you have the focal mechanism for stress and movement tensors. So this is basically the output of the entire process which we are doing. Then second is the type of surface wave tomography, SWT, in which we are making use of surface wave dispersion of regional and teleseismic events. That is the events which are coming from the far off, which are becoming almost vertical as they are being received at the receivers. These events and obviously Rayleigh wave dispersion properties are being made use of to make the VS curves there. Then we have autocorrelation and P and S wave coda from local seismic events that arrive nearly vertical at each station for RWPSI. So this is another part of integrated passive seismic which is being done. And then you have noise based seismic. So in this we are doing cross correlation of long time series of pure ambient seismic noise. So this pure ambient seismic noise is not related to the earthquakes, etc., etc. It is from various anthropological activities or natural activities. It is being cross correlated, and we are again having this 3D VS model of the subsurface. Installation and acquisition is very simple. We are basically putting these small receivers. These are 0.1 to 100 hertz bandwidth receivers. We are making small holes. Holes can be 1 meter, 2 meter, up to 8 to 9 meters also, depending on the competence of the soil, compactness of the soil. We make these holes, put these receivers, they are 3 component receivers, and they are then connected to the seismic recorders. Now these seismic recorders are continuous recording type recorders, very what we call ultra low power consumption. So a single battery, for example, can last for around 2 months of time for recording. Okay, and then we put the whole thing like this in a barrel and then cover the barrel. This is what remains on site for whatever months the recording is being done. So that is the entire footprint of your installation on the ground when we are doing the recording. Processing workflow is again, I'll not go in the details of it. We are very much here in the exhibition hall. Anyone wants more detail can come, because I'm left with 4 minutes, so I'll rather spend it judicially. But we have local earthquake tomography, ambient noise tomography, surface wave tomography. This is the processing flow, and ultimately the main deliverable is this. As I said, 3D P wave velocity cube, 3D VP upon VS cube, seismic event location and focal mechanism, and virtual reflection passive seismic. This is what ultimately becomes the deliverable out of all this processing. This data, this model, which ultimately is derived, also can be used to reprocess your existing seismic, all right, which might be poor because of whatever reason. So this is one example where the seismic was processed, okay, filtered migration, but then later it was processed with the VP model which was created based on passive seismic, and you can see the improvement which has taken place between the two. So this is another very good application of this data which is being generated. Now left with 3 minutes 55 seconds, I'll come to my conclusions, because I have got 5 slides of conclusions, so it's slightly long, so I'll exhaust my 3 minutes in that. So what are the advantages? Why at all we are talking about it? First of all, when we talk about passive seismic, we always maintain that if you are able to do a good seismic in any area, that should be your choice number 1. Passive seismic is not replacing your conventional seismic anywhere. We are talking of passive seismic in the areas where it is not possible to do your active seismic because of geological constraints or because of logistic constraints. That's where we are pitching it, okay? So it is easily applicable in areas with accessibility limitations or difficult operational conditions, because there is standalone stations recording for certain period of time, very small crews. We are able to work in areas like near Brahmaputra, or even abroad. We are working in the completely undulated areas where people can only go with boat, etc., etc. So difficult accessibility area, this is something which is great. Environment friendly. So no active source is involved, so receivers installed and uninstalled, leaving no environmental footprint. For example, recently we finished a project for Oil India Limited, where a lot of stations were put in the reserve forest area. Now in reserve forest area, you can't do anything else, but we were able to put these stations. As you can see, this is the station when it is recording, and this is the station once we have left from there. So there is practically no environmental footprint of this technology. It is extremely cost effective. So you get seismic velocity models at the cost of non-seismic methodology. So if you have a large area, like we are talking of, hundreds and thousands of square kilometers of area, you want to focus on which area to actually pursue with let's say your conventional 3D seismic or 2D seismic. The entire large area can be very quickly investigated using passive seismic in a very economical way, and then the area can be targeted for the remaining part of it. Now, it is insensitive to penetration issues due to high velocity layers close to the surface, or high velocity effects that are common in thrust belt zones, basaltic environment, etc., which active seismic has a limitation. Reason for that is earthquake constitute high energy sources lying within or below the target. See, in active seismic, we are sending the signal from top, and then we are trying to receive the reflection, and obviously these kind of geological situations create issues there. Here we are recording the signals which are below our target, the micro earthquakes, and that's why we are not sensitive to these kind of penetration issues. Directly interpretable results, that is P and S wave velocity models as well as Poisson's ratio distribution below the area of interest. That is what we get. So you have VP, you have VP upon VS. So that is in your area of interest, and we are having direct depth. It's not the time, right? It's not a travel time, it's the direct depth. And results can be correlated with other existing data. So for example, this is one example of correlation with the existing geological cross section, which was built based on available well log data. You get structural and lithological information of unexplored areas. So P wave velocity models can be related to structure, while VP upon VS are lithological characteristic of the study area. So whenever we have large unexplored areas which we are finding it difficult to explore, this is the method which can come to rescue. Stress and fault information. So local earthquake fault mechanism provides information about active fault characteristic and stress fields in the area of interest. Now, it aids in well placement because passive seismic results can be used as complementary information to minimize drilling risk as a reliable alternative solution in case of poor or no conventional seismic. So here what we do is we take the range of VP and VP upon VS, which have been found to be favorable in the comparable areas, and then we can put these points on our data and see which are the points which are favorable. It is extremely helpful in improving the poor quality active seismic data. So you can reprocess your passive seismic velocity models. So this is one example. This was the velocity model which was assumed, and then this was the velocity model which was based on passive seismic, and you can see the improvement in the process results when velocity models have been used. You can correlate this with your existing data. So for example, you have P wave velocity, you have Poisson's ratio, you have density coming from gravity, you have resistivity coming from MT, and then we can have a multi-parametric analysis when we can give different ranges of the parameter for density, resistivity, VP upon VS and VP, and choose which are the favorable location in the entire horizon which are suitable for hydrocarbon exploration. So this is coming to the conclusion because my time is up. So in 30 minutes I will conclude that 30 seconds, I'm sorry, 30 seconds, right? 30 minutes I'll eat time of two more speakers. So this is insensitive to penetration problem, easy application in accessibility problem areas, environment friendly, cost effective, direct interpretable results, structural lithological information on unexplored areas, stress fault information, aid in vent placement, improvement of poor quality conventional seismic, and correlation with other available data. Thank you very much for your attention, and this is my email ID, and we are very much here in the exhibition hall also. Anyone wants to visit and discuss more, you are more than welcome. Thank you, Mr. Chairman. Thanks everyone.